Hello, everyone, and welcome back to today's session. So today what we are going to do is we are going to do a number of examples on 2D frames, and I hope that this video lecture helped you to work on the final homework that is homework number 9. And so let's get started. So in this lecture, we are trying to use we will try to use the matrix method to solve the problem. So it's a more algebraic approach. But in the following lectures, I will also show you some more approaches where we will directly try to use the physical meaning of the stiffness, uh, like stiffness coefficients, and so we can solve these problems also in a different way. So let's first start with the algebraic method that we are going to use in this lecture. Um, so first, I want to recap some of the important concept about 2D frames. And so we actually looked at this 2D frame element in the last class. So the idea here is we have a frame element that is like oriented at some angle, and we are considering like a 2D frame element. So we are only considering in like the element is in the XY space. So there is no Z coordinate if you think. This is a frame element, and the degrees of freedom are actually, if you see, they're aligned in the global X and Y direction. So degrees of freedom are ui, vi, theta I, uj, vj, theta j. And theta j, the degree of freedom is in the Z direction. So if you think we are using the right-hand rule, so anti-clockwise direction is the positive direction. And the load vector is P, and P is related to the displacement vector by stiffness matrix K, and we also need to add the fixed end forces P0. And always remember that P0 are also in the global system, so they are expressed in the global X and Y directions, and both at I end at J end. And this is how we can write the equilibrium for a 2D frame element. And we need to figure out what is K and what is P0. And what we did in the last class is we also represent this frame element both in local and global coordinate system. So you can see that for in the local coordinate system, the local axis goes from I to J. So this is the local x-axis, and there is a local y-axis. And we can put the degrees of freedom in the local coordinate system, in which case you can see u and vi are actually in the local axis. So ui is actually towards the x direction, and vi is actually towards the local y direction. So it's not in the global directions anymore. And similarly, the degrees of freedom at the j end are also in the local directions. And we can write the equilibrium in this local with respect to this local coordinate system. So we can write P is equal to K P bar. I'm using bar means it's a local coordinate system. So P bar is equal to K bar times D bar plus PO bar. And this is easy to write because this is nothing but a beam element. So this is, you can think in the local coordinate system, the frame element and beam element are the same. And but what we are interested in getting this equilibrium in the global coordinate system. But this is what we are looking for. And we said that in the last class we can relate these local and global coordinate system to some transformation matrices. And the first thing is, in the local coordinate system, beam and frame element are the same. So there is no difference between a beam and frame element. And of course, in this case, for this kind of beam element, I'm using the axial degrees of freedom also. So I'm using a 6x6 beam element. Okay, so they are all there. This beam element also have axial degrees of freedom. So this is a very important thing you want to always remember, that so in the local coordinate system, beam and frame element are exactly the same, and there is no difference in the forces or degrees of freedom or the fixed end forces. They're all same. And then we introduce the concept of this transformation matrix. And the transformation matrices, in our case, when we are doing the problems by hand, instead of using lambdas, we'll use the orientation angles like theta, and we'll try to find what is cos theta and sine theta. So but these are the same things. So we'll try to work with this 6x6 transformation matrix. And using a transformation matrix, we saw that we can relate the quantities in the global and local coordinate systems. So P bar is, for example, T times P, and D bar is T times D. And similarly, we can do the inverse transformation of these relationship, and then we can write P is equal to T transpose P bar and D is equal to T transpose D bar. So these are important relationships that you would like to remember. And in this case, one of the important property was that T inverse was equal to T transpose. This means that T is the orthogonal matrix. And one of the physical reasoning behind it, why this matrix is the orthogonal matrix, is because the coordinate transformation actually represents the rotation of axes. So in one case, what we are doing when we go from, let's say, this global x and y axis to the local x and y axis, we are actually just rotating the axis. And because of that rotation behind it, this transformation matrix turns out to be orthogonal. So this is like a physical reasoning why it turns out to be orthogonal. And then we said in the last class, we can relate the quantities in the local coordinate system with the global coordinate system, and we actually come up with these relationships. So if we have the quantities in the local coordinate system, that is the beam element or the frame element in the local coordinate system. In the global coordinate system, we can write K is equal to T transpose K bar T, and P0 is equal to T transpose P0 bar. So K bar and P0 bar are easy quantities, but what we need is K and P0, because these are the quantities that we need to assemble when we are trying to assemble the stiffness matrix for the entire structure. So we need K and P0. And finally, in the once we have K and P0, we can write the equilibrium of a member in the global coordinate system. That is P is equal to KD plus P0. So these are important relationships we have to remember. And after we solve the problem, let's say after we solve all the displacements that we need, we have to go back and calculate the member forces. When we are calculating the member forces, remember that we will calculate the member forces in the local coordinate system. Okay, so this is the quantity we will try to calculate, that is P bar. And I will tell you a reason why we want to calculate P bar, because P bar makes more physical sense compared to P when we are calculating the member forces. And that's the reason we want to calculate P bar, not P. So let me also give you, so this calculation T transpose K bar T, I actually did the calculation, and so this is what the matrix look like if in the global coordinate system. So this is the stiffness matrix of a frame element in which I'm assuming that the orientation angle is theta, and remember that theta is measured from the global x-axis to the local x-axis, moving in the anti-clockwise direction. So this is the angle theta. So if you have the angle theta, you can calculate sines and cosines, and we can do this calculation T transpose K bar T, and this is what we end up. Okay, so I'm going to use this matrix directly in the lecture today. So I'm not going to like do that multiplication, so because I've already done it once. And this matrix is symmetric. So this is a symmetric matrix. It's a 6x6 stiffness matrix for a frame element. And the important thing also to remember is that the degrees of freedom are arranged at the I knows degrees of freedom and the J know degrees of freedom. So they are arranged as follows. So the first degree of freedom is Ui, then Vi, theta I, and then Uj, Vj, theta J. Okay, so this ordering is important. Okay, because this ordering will help us to connect the global and local degree, like to like assemble this element into a global system. And we can also relate the fixed end forces. So fixed end forces in the local coordinate system are actually, these are the numbers that are given to us. Okay, so for given loading, I have given you all like a lot of cases. So what we have is the fixed end forces in the local coordinate system, but what we want is the fixed end forces in the global coordinate system. So we can just do this algebra here. So we can take the fixed end forces in the local. So these are given to us, and we just multiply by this transformation matrix to get the fixed end forces in the global coordinate system. And these are the numbers that are need to be assembled when we are assembling the global system. And another, I just again want to emphasize that if you think like a frame element with the orientation angle 0, it means that the global and local coordinates for that frame element are the same. So you can think that a frame element with theta is equal to 0, it's actually a beam element. Okay, it's the same as beam element, and in this case the local and global coordinates are going to be the same, So you can think that the C is 1 and S is 0. So the transformation matrix is actually an identity matrix. Okay, so this is a special case where the orientation angle is 0. And again, for this case, you can see that P0 is equal to P0 bar, and K is equal to K bar. So this is the case for if you have a beam. So a lot of times, if we have in 2D frames, we have like horizontal members. You can always choose I node. The left side as the I node and the right side as the J node, and then you will have theta is equal to 0, and then you don't have to do any transformation because your transformation matrix will be identity. So your K is going to be K bar and P0 is equal to P0 bar. So this is a special case. Always remember for theta is equal to 0. Okay. So now these are the important steps that we have to follow if we are trying to solve a problem by a stiffness matrix method. So these are the same steps that we have done for trusses also, and for beams also, but they're a little bit, there are few important things that we have to remember here. So the first step is we discretize the system and assign the degrees of freedom. And when we are assigning the degrees of freedom, they are always in GCS, and this is the way we have always done even for 2D trusses. And then we find the element stiffness matrices in global coordinate system, and the fixed end forces also in GCS. And after we find these stiffness matrices and fixed end forces, we have to assemble the global system. It's again in GCS. And then we apply the boundary conditions and then solve for the unknown displacements and the support reactions. So all these quantities were in GCS. Okay. The important thing here is what we have to do is when we are trying to find the member forces after solving the system, we want to find the system member forces in the local coordinate system. Okay, we don't want to find the member forces in the global coordinate system. So if I go back, I can either do this calculation for member forces, or I can do this calculation. So what we want to do is in the LCS. We don't want to do this in the GCS. And just because in the LCS it makes more physical sense, that's the reason we want to do this. Okay. So with this, let's start the first example for our class. And in this case, this is a simple frame in which there are two members, and there is a load that is acting in the lateral direction of 5 kips, and there's no other load on this member. So the properties of these members are given. So E is 29,000 KSI, I for both members is 500, and area is 10 inch square. And the units we are going to use for this problem are kips and inches. So you can see that some of the information is given to you in fit. So we have to convert the units carefully. Okay. So whenever you are solving these problems, just to make sure that you're using a consistent unit system. So, and in this problem, then we want to find the unknown displacements, member forces, and the support reactions. So we typically want to find all the information that we can find. So let's get started. So first step is discretize the system and assign the degrees of freedom. So in this case, we are discretizing into two elements. So one element is AB. So it's like a beam element. And the second member is actually a column member, that is BC. And we are assigning the degrees of freedom. So if I go back and think about what are the free degrees of freedom, you can see that at the node B, there's a node B here. There's a node at B here, and there are 3 degrees of freedom at this node. So one is the X degree, motion, like a displacement in the X direction, displacement in the Y direction, and the rotation. And then there is one free degree of freedom that is a horizontal motion at A and the rotation at A. So there are 2 free degrees of freedom at A. And in total, then there are like 5 free degrees of freedom. So I'm going to label the free degrees of freedom first, and then supported degrees of freedom. So this is my labeling strategy. So 1 is the horizontal degree of freedom, 2 is the vertical degree of freedom, 3 is the rotation at B, and the 4th is the free degree of freedom, like a horizontal degree of freedom at A, and the 5th is the rotation at A, and 6th is the supported degree of freedom. Okay, 6, 7, 8, 9, they're all supported. So all 7, 8, 9 are again supported degree of freedom, and U6 is also supported. So there are 5 free degrees of freedom, and rest are supported. And then we move on, and the next step is to find the element stiffness matrices. And so let's do that. And we want to find the element stiffness matrices and fixed end forces if applicable. So in this case, there are no fixed end forces because there are no member loads applied for any of these members. So let's go one by one and calculate the element stiffness matrices. So for member AB, so first we are calculating for member AB. I'm considering the left node as I node and the right node as J node. So actually orientation angle for this is theta is equal to 0. So it's actually the simple case of, so this member is just a beam member because C is 1, S is 0. And so I can find what is the stiffness matrix. So this is a 6x6 stiffness matrix for this member. And but we have to put the correct degrees of freedom. So you remember that degrees of freedom goes from first I node degrees of freedom and then the J node degree of freedom. And the I node degree of freedom should be UI, VI, theta I, UJ, VJ, theta J. So if you see what is the UI degree of freedom is actually U4, VI degree of freedom is U6, and theta J degree of freedom is U5. So the ordering is actually 4, 6, 5. It's 4, 6, 5, and then 1, 2, 3. This is UJ, VJ, theta J. Okay, so this is how the degree of freedom ordering is, or the label goes. Once you label this degree of freedom, this is important. So make sure that you pay adequate attention when you are labeling these degrees of freedom. And for the second member, I consider a B node as the I node, and the J node is actually the C at C. So you can see that in this case, the orientation angle is 270 degrees. And then C is 0, S is -1. So once we have the orientation, we can calculate these numbers. And actually with this, I use this. So let me go back. So I use this expression to calculate the stiffness matrix. Okay, so C is -1, S is 0 for this case. I plug in the values for this member, and I got this stiffness matrix. So this is the stiffness matrix we got. And finally, I want to put the ordering. So ordering should be, first we look at the I node degrees of freedom. That will be UI, VI, theta I, and then UJ, VJ, theta J. So I know degrees of freedom are actually U1, U2, U3. So it's 1, 2, 3, and then 7, 8, 9, 7, 8, 9. Okay. So these are the I node and J node degrees of freedom, and then we have this stiffness matrix for this member. Now you can see that these both stiffness matrices are written in the global coordinate system. Okay. And then we are in business, so we can now assemble the system and solve the system. So this is the assembly of the system. So you can see that in the 1 degree of freedom, so we have like 5 degree of freedom. So this P1 to P5 is actually the PF, and U1 to U5 is UF. We don't have any POF in this case, or POS in this case, because there is no loads that are acting on the member. So our POF or POS is 0. And actually, I have assembled the entire stiffness matrix. We don't need it. We just need the KFF portion, because we don't need this portion because US is 0. So you can see that U6, U7, U8, U9, they're all 0. So, and we want to calculate our UF, that is U1 to U5. So we have to just calculate this using this relationship here. So we have used the same relationship for trusses and beams. And so this is, nothing is changing. It's the same relationship we have for these kind of structures also. So we are trying to solve for PF is equal to KFF UF plus. So all this KFS US plus POF, this portion is actually 0 in this case. So I just showed you in red just to emphasize that these terms are not there. So we just do the KFF inverse and multiplied by PF, and that's what we will get for our answer. If we solve the problem, this is the answer we will get. Okay. One other observation is you can see that only P1 was the non-zero number here. So P1 was 5 because there were 5 Kips force acting in the U1 direction. All the other forces were 0. So our PF only was 1 entry is non-zero. And after we find the solution, I also wrote what is U1. So U1 was actually UB. U2 was VB. It's a vertical displacement at B. U3 is the rotation at B. So I'm using the correct units also when I'm writing the answers. So the first two are inches, the third is in radians. U4 was actually UA, so it's a horizontal displacement at A. So this is inches. Again, the units are in inches. And U5 was the rotation. Okay, so this is like a radian. Okay, so I have to be careful with the units that I'm using to write these answers. With this, we can go ahead and find the support reactions. So this is the expression for support reactions. Again, remember that in this case, we don't need KSS, US, or POS because POS is 0, and similarly, US is 0. So we really don't need KSS portion of the stiffness matrix. So only calculation we have to do is KSF, UF. And if we do the calculation, we'll find the support reactions. So support reactions will give us P6, 7, and P7, P8, and P9. And I have shown here all the support reactions. Okay. Clearly, when you can check the equilibrium of all these forces, they should all be under equilibrium. So you can easily check like the horizontal forces. You can see that P7 cancels actually P5, and P6 cancels P8. So they are in horizontal and vertical equilibrium, but you still have to check the equilibrium of the moments. You can do a little algebra to see that, okay, this will be under equilibrium. So all the fixed end forces, all the support reactions and the applied forces are under equilibrium. And with this, we can go ahead and calculate what are the member forces. And okay, I also want to show you the displace configuration. So this is how the frame actually looks like when it displaces under that load. And this I actually plotted using the MATLAB code that I have. So just to show you how the frame deforms. And actually, this is by using a magnification factor of 50. So I'm using a lot of magnification factor here to plot the deformed shape. Now, we also want to calculate the member forces in this case. So we always remember that member forces we are trying to calculate in the local coordinate system. So this is what we want to calculate. P bar is equal to K bar D bar plus PO bar. So I just draw this this beam and show the displacement, degrees of freedom, and the forces just for convenience. So you can see that member AB. So we have to do this calculation here. Okay. So we have to calculate the stiffness matrix time multiplied by the displacement in the local coordinate system plus the fixed end forces in the local coordinate system. So for member AB, actually, if you recall, because theta was 0, so in this case, this I node was this, J node was this, theta was 0. So local and global coordinate system were same. So K bar was just equal to K. So the stiffness matrix in the global and local coordinate system were same. So we just use the stiffness matrix that we calculated earlier here. So this is the forces in the local coordinate system, stiffness matrix times just the displacement vector. So we need the displacement vector here in the local coordinate system. So we need ui, vi, theta I, uj, vj, theta j. So here I'm just using, I'm just getting these numbers by inspection. So if I go to the I node, so ui is actually, if I look at the degree of freedom, ui was actually u4, vi was u6, and theta I was u5. So these are the I node degrees of freedom. So these are the 3 I node degrees of freedom. And finally, uj was u1. Vj was u2, and theta j was u3. So I connected like the local and global degrees of freedom in this way by just visually looking at it. And we did, then we have to do this multiplication, and then we can get the answer. So this is the answer we get for the member forces. And I have shown these member forces in this figure here. So you can see that first number is PXI. So PXI is actually 0. Second is PYI. This is minus 1.874. Third is 0. This is the moment here. And the fourth number is PXJ. That is also 0. And then the fifth number is PYJ. This is 1.874. And the last number is this moment here, minus 449.7. So this is, the units are kip inches. Okay, I didn't put the units here, but the units are clear from the problem itself. What are the units? So I've shown the units in this figure. So you can see that this member is also under equilibrium. Okay. So if you check the quick equilibrium, it will turn out the system is under equilibrium. So this element is also under equilibrium. And then we also want to find the member forces for member BC. This is in this case, actually, we have to do the calculation because the stiffness matrix in the global and local system are different. So we have to find the stiffness matrix in the local coordinate system. So this is the stiffness matrix. I didn't wrote down all the entries in the stiffness matrix. It turns out we don't need the last 3 columns, so I didn't put those entries. And we'll see in a moment why we don't need it. Turns out these last 3 columns get multiplied by 0. And again, we have to find what is ui vi theta I and uj vj theta j for this case. So if you recall, for this column member, we considered the top node as the I node and the bottom node as the j node. So actually we are, so if I look at this, so this is how the I node is. So this is the I node, this is the j node. And so what I have done is I have taken this configuration and rotated it in the right fashion. So this is the I node, j node. So x, local x this way points actually vertically downward, and y is in actually the right direction. So you can see that ui and vi. So this is how we will know what is ui and vi is. So if you think very carefully, in this case, ui is actually minus u2 degree of freedom. Okay. So I'm just doing by inspection here. I'm not using, so I can just see that ui degree of freedom is actually minus u2. And vi degree of freedom is actually u1. And theta I degree of freedom is actually u3. So these are the first 3 degrees of freedom. And the last 3 degrees of freedom are actually uj, vj, theta j. Because this end is fixed, they're all 0. Okay. So the last 3 degrees of freedom are all 0. And that's the reason I didn't put the values of these last 3 columns, because they get multiplied by these 3 zeros. So, and we do the algebra, and we'll get the forces. So these are the member forces. And I've shown here the member forces, how they look like. So remember that because the x direction goes down. So this is at the, if we look at the I node, this is pxi. So it's 1.874. Pyi is 5, and this is the moment. And similarly, pxj is minus 1.874, and pyi is, pyj is minus 5, and this is the moment. Okay. So clearly, if you think about it, this member is under compression, and we also have the shear forces and the moments for this member. So if we want to draw the shear force, compression, or like shear force, axial force, or moment diagram, we can do that. And that is typically what is needed for design, but we are not going to draw these in our class. But this information is sufficient enough to draw the shear force, bending moment diagrams. And this is the solution for this problem. One important thing I want to add here is, in this case, the member forces were 0. Okay, so this PO vector was 0, but in other cases, we'll see that the member forces will be there. So we have to add this contribution also. So we'll see in later examples when this happens. But for this example, the member force contribution was 0, or the fixed end force contribution was 0. So let's move forward and let's do another example. And this is another example in which case I have a member that is inclined. That is like, so this is not a vertical or horizontal member. So AB member is actually like an inclined member. And then there is a BC. So it's like a beam member here. So we have 2 members here. And in this case, their member forces. So AB member, there is a 20 kips acting at center. So so this load is acting at the center of this span here. And the BC on member BC, there is actually uniformly distributed load of 3 kip per foot. Okay, and at C, there is a support displacement that is 0.4 inches upwards, and at A, the support moves to the right by 0.25 inches. So there's some support settlements going on, and the dimensions are given, and we want to solve this system. The properties of both members are same. They're given here. And so we want to find the displacements at B, because that's the only location where the unknown displacements are. And we want to find the member forces and support reactions. So we want to actually calculate everything for this case. Again, we have to be very careful with the unit system. and we are going to use kips and inches for this example. So we have to convert some of these units. So we have to convert like 3 kip fit to 3, like 3 so 3 divided by 12. It will become 3 divided by 12 kip inches. Okay, so we have to convert the units of this uniformly distributed load, and we have to also convert this units of length from feet to inches. So you have to be a little bit consistent when we are using a unit system correctly. So let's get started. So first we want to assign the degrees of freedom. So in this case, you can see that we are going to discretize into 2 elements. One will be AB and one will be BC, and we'll put the node at A, B, and C. And we want to assign the degrees of freedom. And the free degrees of freedom are only at B. So we will have 3 free degrees of freedom, 1 horizontal, 1 vertical, and 1 rotation. And but we will still need the horizontal degree of freedom here and the vertical degree of freedom here to take into account these two displacements. So let me show you all the degrees of freedom. So these are the degrees of freedom I'm assigning. So these are the degrees of freedom 1, 2, 3. So U1, U2, U3 are the free degrees of freedom. Those are the ones that are assigned first. And then U5, U4, U5, U6 are the supported degrees of freedom. And similarly, U7, U8, U9 are the supported degrees of freedom. Again, on U4 and U8 are non-zero. Okay, so there are 2 non-zero supported degrees of freedom in this case. So next step is we want to find the element stiffness matrices. So we will go one by one and find the element stiffness matrix. So this is the stiffness matrix for member AB. For member AB, I'm considering A as the I node and B as the J node. So once we have this, we can calculate what are the sines and cosines. So we need C and S. So these are the C and S values. And this is the stiffness matrix. And again, this stiffness matrix is actually, I'm directly using this expression that we saw, like a big matrix here. So I'm directly using this expression to get my stiffness matrix, okay? Because it's in terms of CNS. So I'm just using these numbers directly. So now, after we get the stiffness matrix in the global coordinate system, we have to write down the correct degrees of freedom labeling here. So the label goes, we look at the I degree of freedom first and find what is UI, VI, and theta I. So it will be 4, 5, and 6, 4, 5, and 6. And then the J degrees of freedom, J node degrees of freedom, that will be 1, 2, and 3, 1, 2, and 3. So this is the correct labeling for this element. And this is the stiffness matrix for this member. And because there is a load acting on this member, so we also have to find the member forces or fixed end member forces for this member. So there is a 20 kips force acting. So if we try to do the algebra and we find the fixed end forces, it turns out, so we are using this case here. So I already given you this case here. So there's only shear and moment at both ends. And so you can see that in the local coordinate system, so you can see that we can just directly use these numbers here. So in the local coordinate system, this is the I node, this is the J node. So X direction force is actually the axial. So there is no axial force. This is 0. So you can think that xi component is 0, and similarly pxj component is 0. There is no axial force. The shear at in the I node is actually 10. So this is just 20 by 2, 10, and the moment is 750. And similarly, the shear here is 10 and the moment is minus 750. So local coordinate system, we can directly use these numbers, okay? But what we are interested in the global coordinate system. So we are interested in the quantities in the global coordinate system that are in the X and Y direction, okay? Global X and Y direction. So what we can do is we can write down what is the transformation matrix for this element. And we can take these numbers and multiply by T transpose to get the numbers in the global coordinate system. So first we have to write down these numbers in the correct order. So the numbers that we want to put is Pxi, Pyi, Mi, Pxj, Pyj, Mj in the local coordinate system. So you can see that this is 0, 10, 750, 0, 10, 750, and then 0, 10, minus 750, 0, 10, minus 750. And we are going to multiply with this T transpose matrix for this member. And we get the numbers in the global coordinate system. In the global coordinate system, again, this is Px, PXI, PYI, MI, PXJ, PYJ, MJ. So I and J degrees of freedom. And so you can see that I'm now writing the numbers in the global coordinate system. So this is -6, 8, 750, and then -6, 8, 750. Actually, there's a typo here. There should be -750. So I'll fix this typo on the slide later on. So there should be minus sign here. So I forgot to put the minus sign. Again, the ordering of these degrees of freedom remains the same. So this is 4, 5, 6, 1, 2, 3. So this is the same ordering as here. So what we did this calculation, it was the calculation I was showing you. Let me go back a little bit just to tell you where it comes from. So this is the calculation I was showing you here. Okay. So we have these numbers in the local coordinate system, but we want these numbers in the global coordinate system. And we did this calculation from going from local to the global. So this is how we get the fixed end forces in the global coordinate system using the fixed end forces in the local coordinate system. So we have to do some algebra here. Once we have these numbers, these are the numbers in the global coordinate system that we need to assemble. But let's finish this problem by calculating the element stiffness matrix for this another member. Oh, before I do that, let me tell you what is happening in this transformation. Actually, what we are doing is actually you can think that these are the numbers. The green color was the like the shear force in the local coordinate system. So we are actually taking the x and y component. This is all we are doing. Okay. So if you think the x component is actually -6 and the y component is 8. Because the force was in this direction, x component was actually in the negative x direction. That's the reason I was putting a -6 here. So, and similarly, we were calculating the x and y component of this 10, and actually it turns out to be -6 and 8. Okay, and that's the reason this is the same calculation that we did here. So actually, if you don't want to do this lengthy calculation, you can actually just do the component analysis and get the numbers, but you'll get the same numbers anyways. And these are the numbers again. I'm showing you this is the same number as like here in the global coordinate system, but you can just do by taking components of these forces in the x and y directions. And next, we want to calculate the element stiffness matrix for member BC. In this case, I'm considering the left node, the B node as the I node, and the C node as the J node. So actually, orientation angle of theta is equal to 0 degrees. So in this case, the local and global are the same. So we don't have to worry too much about it, and we can just use a 6x6 beam element stiffness matrix. This is a beam element stiffness matrix for that is the same in the global and local. And the degrees of freedom should be first the I node degrees of freedom, that will be UI, VI, theta I. So it will be 1, 2, 3, and then 7, 8, 9. So 1, 2, 3, 7, 8, 9. So this is the ordering here. And then we can go ahead and find the member fixed end member forces also. Again, because the orientation angle is 0, the transformation matrix is actually 1. And the forces in the global and local coordinate system are exactly the same. Again, there's a little typo here. I forgot to put the negative sign here, so it should be negative 1200. But the numbers here are correct, actually. So again, you can see the transformation matrix's identity. And these are the fixed end forces you get from this kind of distribution. Again, the axial force is 0. And the shear is 30. And the movement is 1200 kipinch. Okay, so make sure that you use the correct unit. So I'm using kips and inches. So just make sure that you don't make a mistake in the units. And the ordering should be 1, 2, 3, 7, 8, 9. So it's the same ordering that we used here. And once we have these two element stiffness matrices and this PO vector in the global coordinate system, we assemble into a big global system. So this is what a global system assembly will look like. So these are all the loads here. So P1, P2, P3 are actually the PF, because U1, U2, U3 are the UF. So these are PF, and these are all 0. So there is no nodal load applied in this case. Okay. But we have POF in this case. So PO is vectors there. So I have to assemble this. We have to assemble this PO vector in this case. So you can see that the KFF is just a 3 by 3 corner here. So this is the KFF matrix. But so in this case, actually U4 and U8 are non-zero. Okay, so actually we'll need this. This block here. So this is the fourth column, and we will also need the eighth column because the eighth entry is non-zero, because these three numbers get multiplied by U4 and these three numbers get multiplied by U8 if you do the calculation. Okay, so I've shown you all the numbers, but we really don't need these numbers here because they get multiplied by zero entries here. So if we try to do the calculation for UF, this is the system we have to solve. So again, in this case, PF is 0, KFF is this block here, and KFS US we can do in selectively. Okay, so we can just take this vector multiplied by U4 plus this vector multiplied by U8. That will give us KFS US plus POF. POF is these first three numbers. And we can solve this system to find what are the U1, U2, U3. So this is the calculation for U1, U2, U3. And so you can see that U1 is U at B, U2 is actually V at B, and U3 is the rotation at B. So sometimes I write it just to give physical significance of these degrees of freedom. And so the first two have the units of inches, the third, the units are radians. Okay. So this is the solution for this problem. And then we can go ahead and find the support reactions. So when we want to find the support reactions, we need the information from POS, KSFUF plus KSSUS. So we have to do the algebra here. And if we do the algebra, this is the answer we'll get. And these are the 6 support reactions. So P4, P5, P6, P7, P8, P9. So we have all the numbers here. Okay. And these are all the numbers I'm showing you for the support reactions. And if we check the equilibrium of these forces, we'll see that these numbers are all in equilibrium. Okay. And then we will move forward. And this is how the displaced configuration of this frame look like. And this is I'm using a magnification factor of 20 to plot this thing. Again, I got this from the MATLAB code that I have. And then we want to go ahead and find the member forces. And now we have to be very careful in finding the member forces, especially for the inclined members, because we want to find the member forces in the local coordinate system. So for member AB, this was the I node, A node was the I node, B was the J node. And we can find the stiffness matrix for this member. So this is like in the local coordinate system, this is just a beam stiffness matrix. So this is a stiffness matrix. The bar is indicating that this is in the local coordinate system. And this is a PO for the PO bar. We already calculated PO bar for this member in the local coordinate system. This calculation we have done when we calculated, let me go back. So when we calculate this member forces, fixed end member forces, this is the calculation of PO bar AB. So we already have this vector here. So, but we have to again calculate this stiffness matrix, okay? Because we have not calculated this stiffness matrix earlier. So we will have to redo some calculations, get these two things. And then what we have actually, first we want to calculate the displacement vector of this member in the global coordinate system. So in the global coordinate system, the displacement vector is actually UI, VI, theta I, UJ, VJ, theta J, okay? And this is the I node. So at the I node degrees of freedom, you can think that UI is actually U4, VI is actually U5, and theta I is U6. And similarly, UJ is U1, VJ is U2, and theta J is U3, okay? So this is the displacement vector of this member, but written in the global coordinate system. And now we have to take this displacement vector and convert to a local coordinate system. The reason is because we want to find the member forces. In the member forces relationship, you need D bar. You don't need D, okay? And to find the displacement vector in the local coordinate system, we just use the transformation again. So we use the transformation matrix. So this is the transformation matrix times D. So we have to do this algebra. So take the transformation matrix and multiply it by this global element displacement vector, and then we will get this answer. And this is in the local coordinate system. And this is what is needed to get multiplied here. So you can see that the algebra is a little tedious if we want to find the member forces, but this is what is needed, and that's how it's done. So after we get this D bar, we can just, we already have all the ingredients to get P bar. So we can just do the multiplication and get our member forces. So if we get the member forces, this is what they look like for this member. And if I try to draw these member forces, so you can see that I'm again using this graphics here to show you where the x's are, local x's are. So actually pxi is actually 61.73 is pxi. Pyi is actually minus 61.73. So this is pxj. So this is pxi, this is pxj. Pyi is actually 8.31. So this is in the y direction. So you can see this is in the y direction. And this is the movement here. Similarly, Pyj is 11.61. So this is 11.61. And if you think very carefully, 11.61 plus 8.39, actually they cancel each other. They cancel with 20 actually, because the total shear is equal to the total force applied on this member. And you can clearly see by looking at the Pxi and Pxj that this member is under compression, and the compressive force is actually 61.73 kips. Okay. And this is another reason why we want to actually find the member forces in the local coordinate system. For instance, if we have calculated the member forces in the global coordinate system, then our px vector will be in the x direction and py vector will be in the global y direction, like horizontal and vertical. And then you can see that horizontal and vertical forces does not make much sense. Okay. What we need is the forces along the axis of the beam and perpendicular to the axis of the beam. That is what we are interested in, because along the axis, that number gives us the tension or compression, and perpendicular to the axis, that gives us the shear, because those are the numbers that are not needed for the design. We don't really need the, for the design purposes, we don't need the numbers in the x direction and y direction. We just need in the local axis. Okay. And that's the reason we want to calculate the member forces always in the local coordinate system, because that makes more physical sense when we are trying to design these structures. So this is the calculation for member AB. And we can go ahead and do the calculation for member BC. Member BC, the calculation is simple because the global and local coordinate system were the same. So we can use the same stiffness matrix that we used earlier for this member. So K bar was actually, we already calculated, that is actually the K matrix. And then we have to plug in the right displacement vectors. So in this case, it's ui vi theta, uj vj theta j. We don't have to do any transformations here because this is already oriented correctly for us. So ui is actually u1, vi is u2, and theta I is u3. So by inspection, we can just put these 3 degrees of freedom, and then we can put uj, vj, theta j. I made a typo here. My answers are correct, but there's a small typo because vj is actually u8. That is non-zero. So I'll fix this typo in the slide later on. So I just want to mention that vj should be u8, and that is non-zero. So that is 0.4. And theta j is 0, uj is 0. And we have to make sure that we add these fixed end forces. And these are the same fixed end forces that we have calculated earlier. So this is not a new calculation. We add them together, and these are the numbers we will get. So this is the answer for this case. So you can see that this is pxi, pyi, mi, and then pxj, pyj, mj. And by looking at it, you can clearly see that this member is also under compression, and the compressive force is actually 56.35 kips. Okay. And with this, we can also draw the bending moment and shear force diagram if needed. So all the calculations can be done that are needed. Now, this is the last example for this session. And in this example, we are going to look at portal frames. And so what's going to happen, we are going to analyze two type of frames. So you can see that on the right side, this is the case A, where we have a frame. So in the frame, there's like, it's a single bay frame. So there's 2 column members, 1 beam member, and there's some kind of a lateral load acting. 50 kips are acting at C, and there is also some distributed load acting on this beam member BC. And the properties of all these members are given here. E is 29,000 KSI. For all these beam and column members, I is 500 inch to power 4, and area is 10 inch square. So again, we have to use a consistent unit system. So for all the following calculations, I will use kips and inches. And on the case B, what I have done is I have introduced a brace member. So brace member, always remember, so brace member is like a truss member. So bracing is nothing but a truss member. So, and the brace member is connected to the frame at the 2 sides by pins or hinges. Okay, so these are 2 hinges here. So hinge at this end, hinges at the other end. Because of the hinge, actually, the movements from the frame cannot get transferred to the braces. So the brace members are under just pure compression or tension. They cannot carry any movements. Okay, so brace members are truss members, and so whenever we have a brace member, we can use the truss member stiffness matrix. That's because we already know what is the stiffness matrix for a truss element. So brace element is modeled as a truss element. And the area for the bracing, I'm using 2.5 inch square for this problem. And we want to solve these 2 cases and to see what happens. And the reason I'm trying to introduce you this idea of braces is actually I want to show you what is the effect of braces. So what this brace member is going to do to this frame. Okay. So let's get started. First, we want to assign the degrees of freedom. And in this case, we are only interested in finding, let's say, unknown displacements. So if you think carefully, the unknown displacements are at B and C in both cases. Okay, B and C, that's where the unknown displacements are. And I'm not interested in finding, for example, member forces and support reactions. We could have calculated, but the calculations are very similar to the first 2 examples. So I don't want to repeat myself too much. So we will just stick with calculating the unknown displacements. So if you want to calculate the unknown displacements, these are the degrees of freedom of interest here. So we are interested in only the free degrees of freedom for now, because all the supported degrees of freedom are 0. So we don't have to consider any supported degrees of freedom. So I'm just showing the free degrees of freedom in the 2 cases. And the degrees of freedom labeling are at the B, it's U1, U2, U3. And at the C node, the degrees of freedom labelings are U4, U5, U6. And actually, I have discretized this frame into 3 elements, 2 columns and 1 beam. For the brace frame, the degrees of freedom are exactly the same. So they're not changing. Okay. So you can see that the bracing does not introduce any additional degrees of freedom. Okay. So there for the bracing, because it's a truss member, we don't need any additional degrees of freedom. All the degrees of freedom are already there. So, but in this, for the base frame, there are 4 elements: 2 column members, 1 beam member, and 1 truss member. Okay. So we have to assemble these 4 elements in this case, and 3 elements in the case of when there is no bracing. So now what we want to do is we'll go ahead and try to find the stiffness matrices of each of these elements and assemble the system together and solve the system. This is the stiffness matrix for member AB. So AB is I'm considering A as the I node and J as the B as the J node. So theta angle is actually 90 degrees. Okay, and so C is 0, S is 1. So with this, I again went back to that big expression of stiffness matrix and put down the entries of the stiffness for this member. But and when I'm labeling it, I just need first is the I node degrees of freedom, and then is the J node degrees of freedom. Actually, I don't really care what is the degrees of freedom at I, because we are the only interested the only degrees of freedom in which we are interested in are actually the J node degrees of freedom that are U. So this is UI, VI, UJ, VJ, theta J. So it's going to be U1, U2, U3. So 1, 2, 3. We don't really care about these degrees of freedom because they does not appear in the calculation, and we will see in a moment. So actually we are interested in this 3x3 block here for this stiffness matrix. The other thing is, if you're doing for the exam, you don't have to write down all the entries here. You can just put this block here, okay? And this is symmetric. So actually you can just put 1, 2, 3, 4, 5, 6 numbers here, because this is symmetric, and so the rest of the numbers come from symmetry. So you can be a little bit efficient when you're doing like problems in the exam or even for homework. So this is the calculation for member AB. Member BC is, this is the I node, this is the J node. So in this case, the global and local system are the same for this member. And so this is the stiffness matrix for a beam element, okay? Because beam and frame are same in the local coordinate system. And finally, the degrees of freedom ordering is the I node degrees of freedom are UI, VI, theta I, and then the J node degrees of freedom, this is uj, vj, theta j. Okay, so these 2 degrees of freedom I put here. So it's actually 1, 2, 3, 4, 5, 6. Okay, so ordering is very simple here, and so we will need all these actually in member, all these coefficients from this element. And we also have to calculate the fixed end forces for this element, so because there is some distributed load acting on this. Again, so this is the calculation of fixed end forces. And again, for this case, the transformation matrix is 1. So global and local PO vector are same. So we don't have to really do this calculation. I'm just showing you that it's there, but these the identity matrix. And the calculation is, so PX is actually 0, PY is 20. So PXI is 0, PYI is 20, and MI is 80. So it's 0, 20, 80. And then at the J node, this is PXI is 0, PY J is 20, so PXJ is 0, PYJ is 20, and then MJ is minus 800. So, and this is transformation matrix is identity issues. So this is the same. So you end up with the same vector in both local and global. And the ordering is 1, 2, 3, 4, 5, 6. So ordering is exactly the same as for the stiffness coefficients. And then we have to go do for member CD. So member CD, I'm using this I node is D, and J node is at C. So angle theta is 90 degrees, and C is 0, S is 1. So this is the calculation. Actually, this is the same. This stiffness matrix for member DC is exactly the same for member AB. Okay, so these numbers are not changing. These are exactly the same numbers that we have calculated for AB. So I'm not redoing the calculation again. Only the I have to just put the correct labels in this case. So the labels that I'm interested in, I'm not interested in any degrees of freedom at I node. The J node degrees of freedom will be uj is u4, vj is u5, and theta j is u6. So it's 4, 5, 6. Okay, and these are actually the, if you look carefully, these are the same numbers as we have done for the other member here. Okay, so they're exactly the same numbers. So you can reuse some of the information you have calculated when you're doing these problems. And finally, with these information, if there is a truss member, we also want to calculate the stiffness coefficient of that truss or bracing member. So this is the calculation for member AC, that was the bracing member. And these are the coefficients. And here I'm considering this as I node, this as J node. So theta is 45 degrees. CNS is both 1/√2. And these are those EA by L times C square, S square, and so on. Those are those coefficients. This is the truss element stiffness matrix. Okay. Again, I'm not interested in the I node degrees of freedom. The J node degrees of freedom that affects are actually 4 and 5. So this will be UI, VI, UJ, VJ. So UJ, VJ are 4 and 5. Okay. See, the truss member does not have a rotational degrees of freedom. So I don't have to worry about U6 here. Okay. So only the truss member is only going to affected by U4 and U5. So I just put UJ is 4 and VJ is 5. So we are interested in actually only this 2x2 block, if you think very carefully on, because this is what we'll get in the KFF matrix here. And always remember, bracing is just a truss member. So this is a truss element stiffness matrix. So finally, I put together for the case A, and for the case A, I'm just assembling 2 columns and 1 beams. Okay, this is the KFF. So this is PF. So PF is equal to KFF plus times UF plus POF. US is 0 in this case, so we don't need KFS. So I didn't did this calculation. Okay, so I'm just writing this relationship here, and US is 0, so I'm not including this these 2 entries in my calculations here. And you can see that I'm just writing half of KFF because it's symmetric. And so in this case, if you think carefully, only P4 among all these P4 was, there was some applied load at this here. It was 50. So P4 is 50 kips. Rest all of the P1 to P6 are all 0, other than the only non-zero entry is P4. And these are the known displacements over UF plus POF. So I have to assemble this these numbers. Okay, this assembly comes from the POF vector that we have. So once we have this system assembled correctly, we can solve for the unknown displacements. So these are the 6 unknown displacements we solve for. So so U1, U2, U3 are actually the displacement at the B node. So actually they are UB, VB, theta B. And U4, U5, U6 are the displacements at the C node. So they are UC, VC, and theta C. So this is how we can get the displacements at B and C node. And next, I also show you the deformed configuration of this in this case. So this is the case A with the no bracing. So you can see that I'm using a magnification factor of 20 here. But you can see there's a lot of lateral displacement in this frame. Okay. So this frame undergoes a lot of lateral displacement. And if you check the number for lateral displacement, so lateral displacement is actually displacement in the U1 or U4 direction. So you can see that U1 and U4 is actually UB or UC. They're very close to each other. So you can think like, let's say if we see U4, it's about 2.86. So it goes under the displacement in the U4 direction is 2.86 for this frame. This is the case B. Where we have actually the bracing. The system is very similar, but we are also assembling the brace element or the truss element, this element stiffness matrix when we are assembling the KFF. So this is the final KFF for this system, and the PF remains the same, and this POF actually remains the same. So these 2 things doesn't change. Of course, we don't have KFS US, so this thing, the term in red is not there. And we can again solve this this system, and these are the displacements we will get. So the displacements are again U1, U2, U3, U4, U5, and U6. And these are the displacements at B and C degrees of freedom. So they are like first 2 are in inches, third are radian, and again 2 inches, and then 1 radian, because radian is the rotation here. But the important thing is you can see that the displacements have actually, the lateral displacements has reduced a lot in this case. So if I show you the displaced configuration, I'm again using the same magnification factor of 20, but the frame is actually displacing in the lateral direction a lot less. And actually you can check that the lateral displacements are reduced by a factor of almost 6 in this case. So this is where the bracings are very effective. And bracings are very important members because they can actually provide lateral stiffness to a frame. So if you want to reduce lateral motions in a frame, you can put like bracings. And actually, when you learn about structural systems in your future classes, or if you happen to take a class on structural systems, they talk about different kind of bracings that can be used, and there are different patterns of using bracings and so on and so forth. But at least now you have an idea how to include bracings in a structural analysis. So if you want to do a structural analysis with a brace frame, you can usually do it now, and you have a good idea how to understand the how to use bracing in the problem. Okay, I hope that this helps you to understand better the system behavior also, but there's much more you can learn about bracings, brace frames, and so on and so forth, but probably those are for future classes. With this, I would like to end the session today, and again, as always, if you have any questions, feel free to reach me, and I will also post the homework that is related to 2D frames. And actually there might be some problems also on beams also, in which we will include the axial degrees of freedom also. And those two kind of problems will be in the last homework, that is homework number 9, and I will try to post it um, as soon as possible. The other thing I would like to mention is that this is a more algebraic way of solving the problem, where we are trying to assemble the stiffness matrix for every element, and then trying to take those stiffness coefficients and put into a global system. But actually, there is a more physics-based approach of solving these problems. Especially that approach is simpler if the members are not inclined. So let's put it this way: if we have a frame member with all members where members are only horizontal and vertical, it turns out we can very easily do these problems by using more physics-based approach. And that is what I will try to explain in the next class. So actually, we will try to solve the same problems using a different approach. And these two approaches are related, okay? And that's approach that we have already used when we were doing beams, actually. So it's a similar approach, and but it's a more direct approach, and it actually also helps you to develop some physical understanding of the problem. And that is what we are going to do in the next lecture. But this information should be enough to help you get started on the homework. So you can use either method, okay? So you can use more algebraic approach, or you can use a more physics-based approach to solve the problems. So everyone